Hey, I think we should be live. I see a couple of people here on the chat already. I see Waleed is here. I see Max is here. Good to see both of you. Uh, Welcome. Uh, this is another stream. It's a continuation of the previous stream. And in the previous stream, we were doing some USB device reverse engineering. And specifically, we were reverse engineering the sort of Windows specific driver for this keyboard, which is a GM MK mechanical keyboard. And yeah, it went pretty well actually. We got a good basis down. We got like the initial part of a driver written. And what we're going to be doing today is just taking that idea further. Um, Now, hey Nate, hey Greg, nice to see you both. So, what we're going to be doing today is actually looking a little bit more at like trying to reverse engineer the profile part of the keyboard. I don't know if I mentioned this last time, but this keyboard has support for profiles, and yeah, in those profiles you can have different key assignments, you can have different LED stuff going on, you can have different macros. I think I haven't actually used them before because I don't use Windows, so I don't know really what you can do with them, but I do know that there are three distinct profiles. There's also key assignment, and this is actually one of the most useful things that I want to get out of this keyboard, because at the moment there's a little bit of like I have to do some configuration using like some of the Linux like behind the scenes tools with like Xmod map and that kind of stuff to do keyboard remapping. But I only really need to like remap like one key basically, uh, which is the tilde. Um, and at the moment, I'm not sure if it's why you can actually see that I've run a script here called tilde, which basically like on the fly inserts that key, like tells my keyboard to remap, not my keyboard, tells Linux to remap the keys and everything so that I have that key. Um, but what I really want is the keyboard to just do it itself because it has that capability. And finally, we've got the macros, and we'll see how far we get with that because it's definitely going to be the most complicated part. But but yeah, like I think that would be super cool to get down because you can actually just say, okay, this key, it doesn't send a key, instead it runs a macro, and the macros are pretty straightforward. It looks like to me, you can basically press keys and you can have some duration between pressing the keys. I thought there might be mouse and that kind of stuff involved because this device presents itself as a USB mouse, and that's how it does the control communication. But as it turns out, there's no mouse to be found here, and so that mouse communication is like a red herring or something. I don't know why. Maybe it's to do with the microcontroller that they use inside. I don't know which microcontroller they use inside here, but it might be like the limitations of that microcontroller's USB like peripheral stack doesn't allow you to like do standard control extensions. I'm not exactly sure, and it doesn't matter in the end because this is how we have to talk to the keyboard. We have to talk to its mouse endpoint. But that's how it is, and that's what we're going to do today. And okay, so just two small pieces of follow up before we get going. I see more people rolling into the chat, so hello everyone. Uh, there's two things I want to follow up on. One, at the end of the last episode or the last video, we were trying to get these LED modes to work so that we could switch between modes, and I was kind of really confused at the end as to why it didn't work. And the reason it didn't work is because I had like copied, like I was scanning through the USB traffic, and I got some data from like one packet later rather than like taking one packet earlier, and that kind of threw the whole pattern out, and I was like, oh, I don't see a pattern anymore, I don't understand how this works. but actually there is a pattern, and the pattern is the same as the brightness, which is what we also reversed. So the in the LED mode, what it turns out, and maybe I didn't put it directly in here, but what it turns out is this C parameter is actually, it's just mode plus, it's just 8 plus mode. That was it. Yeah, and mode is just a number 0, 1, 2, 3. And that's the same as in brightness, right? We had 8 plus level, and in the end we set level. And down here in the mode, it's it's 8 plus mode, and then not mode plus 1, just mode. So that should work now, which is kind of funny. The other thing I just want to mention is that Greg, who's in the chat here, actually submitted a PR just to do some cleanup in the driver itself. And I need to triple check that is what I'm what I've actually got running here in the. Let me just quickly see that. All right, yeah, so these are Greg's changes here. And then basically there are, in the source directory now, there are basically some split files and kind of just cleaned up and set the cleanup process to work in a better way. So I think what I'll do is I'll just put those changes back here. So 08 plus mode, that's just mode. And yeah, I think there wasn't anything else worth keeping in the other one. And we'll just keep this to do. So those are the pieces of follow-up. There's actually one more useful piece of follow-up, and we'll get into this a bit later. But that is, I think I've actually solved the problem of not being able to show the reverse engineering process on the stream. And I say I solved it. Actually, Nate solved it, Nate is also here in the chat. Nate suggested to me to look at Ebpf, which is it's a kind of subsystem within the Linux kernel. And it's kind of amazing. It's this, I hadn't even heard of it before. And maybe I'm the last person in the world to hear of it, but for me it seemed like something that was kind of under the radar. And basically what Ebpf is it's a system in Linux that allows you to hook into basically everything in the kernel and attach your own little piece of code on the fly whenever you want, just from user space. Obviously you need to be root to do that, but you can just basically attach a little program into the kernel. And so what we can do is we can write a program that just hooks into the, like, whenever a USB packet is being processed, and we can just pull out a bunch of data that is useful for us to know in the reverse engineering process, and then we can pass that back. Nur Mohammed says, do you suggest to watch that stream first? I mean, you'll probably get more out of it if you watch that stream first, indeed, but I don't know, you could just try to watch this one, see if it makes some sense. I'll probably, go back over some stuff, but that one covers like a bit of the, initial, like some of how USB works, and I'll probably get back into some of that anyway, but there's definitely some stuff in there. But in this Ebpf mode, basically you can just write a script, run it in not a script in the kernel, you basically write like a small C program, and Ebpf is kind of like a small virtual machine, kind of. There are some caveats to that. And you run this in the kernel, and we can just get some events out. So basically, the problem I was having is that I'm running now 2 cameras, a microphone, the keyboard, a mouse, like a whole bunch of devices, mainly the cameras and the microphone. They are like spamming USB packets like crazy at my system because, of course, they're streaming live video and they're streaming audio. And so USB, like the USB monitoring program that we were using USB Mon plus Wireshark in this configuration. Unfortunately, USB Mon, which is another module in the kernel, it doesn't have the capability to filter like only per one device. And that's really the big problem, is that just because of the whole way that it works with streaming the packets out, you actually have to collect them in this one big buffer. I was running out of space, it was crashing my system. What I'm hoping is today, with this new program I've written, we'll actually be able to just stream only the keyboard traffic, which should be fine, should be completely, I've done a little test, it seemed to work. I haven't done any streaming since then, so it's hard to say. But I think it should work, so I'm pretty excited about that. We're going to see how that goes. All right, so yeah. So again, thank you, Nate, for that. Like, Nate is like a never-ending fountain of wisdom. And if you're not on the Discord, you should join the LRJS Discord, because Nate drops like fire links all the time, and I'm learning a lot. So thank you, Nate. All right. So I guess the first thing to do is I'll just show you this program, this new way of us monitoring traffic, because we're actually going to collect the traffic in real time this time. So let's go to the terminal. Should be seeing the terminal now, and I've got this program called Ebpf USB. And if we look at the help for that, it's for monitoring USB traffic, and you can see that we can filter out based on the vendor ID and or the product ID to basically only get stuff. Nate says that's the nicest way someone has told me that I never shut up. Well, I didn't mean it in that way, but you know, you don't have to shut up. Like it's as far as I'm concerned, it's all gold. So we can filter out based on the vendor ID and the product ID, and there's a couple of other little bits and pieces that we can do, but that's not that important. So what I want to show is just if I run this program, I haven't tried this yet, but this is probably going to be showing a lot of data, so I'll just probably stop this pretty quickly. That's all the USB traffic. Oh god. Control C. Oh god. I should have seen this coming. Alright, maybe I can kill that. Let's grab Ebpf. No. Then it's going to be that one. Operation not permitted, yeah, because all right, good. That was that just got out of control. But you can see that this is the problem, right? Like within that time, we streamed out like 30,000 USB packets, and if we're just looking at trying to grab just like one like little thing that happens on the keyboard and be able to go back and reference it, like that's never going to work. So what we can actually do is just filter on one device. So we can see which devices I have. If I run ls USB, these are all the different devices and hubs that I have. So this is the keyboard right here, and what we can do is we can filter on, product ID, vendor ID, one of those. Since this vendor ID is unique, we can just filter on that. So what I can do is I can run Ebpf again, or the Ebpf USB program, and provide a vendor ID, and the vendor ID is going to be this. And if we do this now we get a much calmer capture, and if I press a key, we can see that we only get data for that. So that's way better. So this is kind of how we're going to do the reverse engineering in this one. And I'm really happy with this. This gives us basically, it's not all the information that we were getting from Wireshark before and from USB 1. But most of that information we don't need, for one. We definitely don't need it today for this device. And I think I'm going to work on this program a little bit more and just try and bring it at least up to the level where all of the information that is available in Wireshark is available in this program as well. But for right now, this is actually perfect. So I'm going to stop that again, and what I'm going to do is I'm going to T this out to a file. If you don't know what T does, what we're doing here is we're piping this output, which is just in the terminal. We're piping this into a program called T, and T kind of splits the stream there, and it shows you stuff on the terminal, but it also allows you to write off to a file. And that's useful because we're going to want to go back and refer to some of these things that are happening. Like, we're going to want to scan through them later. So I'm going to tee off to a file, and I'm just going to call this keyboard usb.log, something like that. And now we're just capturing data. So if I press B a couple of times, that's the data. That's a key pressed, that's a key released. So that's kind of how these things look. And that's it. All right, so let's actually look at how we can do this. What I'm going to do is I'm going to go over to Windows, and Windows is sleeping here but should wake up. You can't see this, but I'm going into the devices menu and I'm going to USB, and I'm just clicking on the USB keyboard so that it passes through to Windows. When I do that, Windows kind of makes a little sound like it recognizes some hardware has been plugged in, and then we can run this program, which is basically the program for configuring this USB keyboard. Yeah, so what we've got up here is the profiles. If I were to click LED editing enabled, we'd get like the LED edit mode open again, so we could go to different modes here, and you see that they are kind of showing here. And if I go to the keyboard itself, you can probably get some vague notion that the keys are changing there. And if I change mode again in this menu, you can see that like we get a new mode there. And yeah, so that's kind of how that works. And if I look back now at the terminal, what we should see is that there's a whole bunch of data there now. And we can actually just I can't actually Control C from there. I'm just gonna run that again because we can kind of start with the blankest slate possible to make things easier. So what we're gonna do is, first of all, I'm going to set the profile to 3. That's the first thing I'm going to do. And then we're going to go and see like what number packet we're on. And we're just going to make a note of it and move to the next one. So this is the process of collecting data. So I click profile 3. If I go back to the terminal here, you'll see that there's now 36 USB packets exchanged. And what I'm going to do is I'm going to go here into VS Code, and I'm going to start a new file, and we'll just write here from 1 to 36. Oh, I can't do that. Okay, at least I know that it's 1 to 36. So 1 to 36, that's going to be set profile to 3. All right, and then I actually pressed the keyboard a couple of times there, so we want to start logging here from 44 next time. And let's go and set the profile to 2. So now we should be on 2. We should see that there are more packets here, so now we're up to 80, and we'll just make another note of that. in here. So 80 set profile 2, and then 81, provided I don't touch anything in the meantime, 81 should be profile 1. And now we're on profile 1. Go back to the terminal here, 116, back to VS Code, 116. This is us setting profile 1. Cool. All right, so that's some information collected there. What is Windows showing me here? Okay. Now we've got some data about the profiles kind of changing. There's something else that we should do in this moment, which is go into another profile and just do something that we already understand, like how it works. So what I'm going to do is I'm going to go into profile 2. I'm going to go into LED edit mode. And I want to tweak the brightness, because I know how the brightness works. At least I know how it works for profile 1, but I want to see, is there something different in profile 2? Does it send the same data? Or does it send something different when we're in profile 2? So I'm going to make a note of where we are in the stream, because this is where it's going to start. So we're starting from packet 157. So I'm going to go here, say 157 till however many. And what I'm going to be doing here is I'm just going to put the brightness to the maximum level. So that's it. Nothing too fancy. So if we go back here, we've sent some packets. We're on 162 now. Switch over, 162. Set brightness to max in profile 2. Okay. That's probably enough data for us to get going now for a little bit, just to like analyze some of this stuff. So what I'm going to do is I'm going to go back to Windows, finding my way around. I'm going to close that, and I'm going to like disconnect from Windows this device because I want to use my keyboard again. And then let's go down here, and we sent a couple more. You can see actually that there are some packets that happen when you disconnect, right? You can see that there are actually some control transfers here to something called endpoint 0. Endpoint 0 is the control endpoint. And so when you disconnect or you do things like that, there's a whole process that the host and the device go through to exchange information. So that's what that is, but we don't care about that. So I'm just going to Control C out of it. And what we can do is we can go into VS Code, and now we've got this nice keyboard log of all the packets, and we can just scan through it in here. I think it's trying to detect what the syntax is. I think I'm just going to say that it's just text, because I don't think that highlight is helping. Yeah, let's have a look at what's going on. So when we set the profile, that consists of 36 packets, which is a lot more than we were sending. In the in like the brightness and the LED edit mode. In those modes, can actually go into this driver code, and we can see that like in LED, in the set brightness mode, we do 3 sets of a command transfer and an interrupt transfer, and both of those are just a transfer. So we do 6 transfers for a brightness setting and 6 transfers for a LED mode setting. So those are like, yeah, like this is like 6 times more actually to do this. You get 36 of these things. So let's have a look at what it consists of. So the first packet, what you can see is that there is an actual length here and a buffer length. So sometimes the actual length will be smaller than the buffer, but we'll still just have loads of zeros. And in this case, the actual length of this data is, well, it's actually only this. It seems, at least anyway. But and remember from the previous section, what I should mention is, do I have it in this thing? I don't. What I'm going to do is just, let's go here quickly here, and I just want to go ls USB and just show you the detailed information about this device. So this device, it has this one interface. Actually, one interface has two interfaces. It's got the keyboard interface, which is this one, and then it's got a mouse interface, which it's not a mouse, it's some kind of control endpoint, control interface, and that has two endpoints. And so what we've got is an out endpoint. So this is where we send data from the computer to the keyboard. It's out from the perspective of the host. So this is our out endpoint, and we have one in endpoint. And the in endpoint is us receiving data from the device. And so yeah, each of these are 64 bytes, which is why you see these 64-byte packets. And you can see here that the keyboard, when it's delivering its input packets, they're only 8 bytes. So that's why you saw when we were playing around with the keyboard that it was only 8 bytes. So these are our two endpoints. That's kind of, I just wanted to make sure that all of that's clear while we're looking at this data, because what we're actually seeing here is this is the packet number. This is the vendor ID, product ID. This is the endpoint. So it's endpoint 3, and it's an out endpoint. And this int tells us that this is an interrupt endpoint. Which is, well, I spoke about this in the last video a bit, but USB has different ways to transfer data. And the way that we transfer data when configuring messages for this keyboard is something using an interrupt endpoint. So we can send data to the keyboard, and the keyboard makes the promise, or we make an agreement with the promise that with the keyboard. Sorry, it's been a bit of a long day. We make an agreement with the keyboard that we will interrupt it every so often and ask it to give us data. And if it has data available, it will give us data. It's a weird concept. It's a weird conception of an interrupt, because most of the time when you think of an interrupt, you think of it the other way around. But that's how it works in USB. So that's what we're seeing here. We're seeing a 64-byte packet, and this is what we're sending to the device. So when we initiate this whole flow of setting the profile, we send this packet. And then we get this packet back. Now, this is one of the things which is missing from like what we saw in Wireshark, which is we would see like both the request and the response. As in every exchange, there's kind of like there's a two-way communication going on for the most part. We don't see that in this view. So what we see is that we made this request. We can assume that the device kind of acknowledged us. And in this case, we can just assume that the host sent an interrupt kind of to the device, and now it's responding. So that's kind of what's going on here in this case. So you can see that this initial part of the packet seems to be the same, but we actually receive a whole bunch of data here. I'm not sure what this data is. Let's see, 55AAFF2450C. I'm not seeing anything that makes a whole lot of sense to me right now, but it could be, and it probably is, something about like kind of configuring what the initial settings are. Like the keyboard is telling us what the state is in this profile, like what LED mode are we in, maybe like what is the refresh rate, what is like, Yeah, I'm actually not sure if like things like the refresh rate change between profiles. That's something we might want to take a little look into. But yeah, okay, in the beginning when you're looking at this stuff, you're not going to get that much of an idea. You kind of have to find the patterns in this stuff, and that's why we collected information from 3 different profiles. Because then we can kind of see what is different between these different things. So that's that. We get a response to it. Then we actually get some more data. Oh no, this is dun, dun, dun. Yeah, so I'm missing packets. That's what I should do. So then we have this third packet, and that one actually has this kind of prelude that we've seen in the previous episode. We always send this kind of header first. That's like the first thing we do. We send 4101, and that might be some specific exchange for certain kinds of human interface device. I'm actually not sure about that. But in any case, we do see this header, and we also see a kind of footer on the other side, which is 04020002. And in the middle is kind of the meat of the transaction. So what we're seeing here is this is some sort of probably status request, like please give me your status for this profile. And this is the device returning us like some information about the status, which we don't really understand. This is the beginning of a transaction. This is kind of an ACK to that, basically, and an acknowledge. And so at this point, packet 5, this is what we would think of as being the beginning of the message, I guess. So 043D, 0005, 38. What we saw in the previous things, in the LEDs and the brightness, was that this second byte here has some information stored in it somehow. And quite often this byte would also have some information stored in it, and the rest would be kind of like a signifier of what kind of mode and what we're editing. What we actually notice is when we do this, we get some more data coming back this time. I'm not sure if it means anything in this case. I'm not sure if this is us like setting profile 3. So maybe there's some information encoded here that says this is profile 3. But what we'll see is we don't get the footer here. So this actually consists of multiple, like it seems to consist of multiple packets. Actually, where is the is there a footer? Yeah, okay, so the footer is here, packet 11. So between, like it starts up here on packet 3, and then we get a response on 4, and packet 5, packet 7, and packet 9 are like information. So this is something that's maybe worth writing down. So packets 1 to 2 status ? And then packets 3 to 12 are like one request, like 3 to 12, let's say request 1. So presumably there's more because this goes to 36. Sorry, I'm just reading the chat here. Patrick mentions, have you seen that I was saying in the previous, in the last stream that the second byte is the sum of the another field? Yes, actually, I have seen that, and also someone else mentioned it before in the stream. And at least in the case of like looking for the LED mode, that turned out not to be the case because I was looking at the wrong packet. So we kind of identified a pattern that was not there, like a false positive in that case. But I do think there is somewhere along the way there is some kind of checksum thing happening. I'm not entirely sure what it is, but it seems that something like that is happening somewhere. Okay, so 13 is the beginning of a new transaction. 4B, so there's more information coming there. Then there's another piece of information, another one after that, even more. Another one. So there's a lot of information going in this transaction. 90 C6. Yeah, and it ends here at 31. Okay, that's interesting. So what did I say? 13 to 30. I guess it's 32, right? Because I want to count the response. So 13 to 32 is what we can think of as being request 2. And then 33, that's interesting. So 33 is a different thing again. So in 33, we send this, then this, and then that was it. That's the end of the exchange. So, like, there's kind of, I don't know if this is like a second, like, little burst of like status, because, oh, so that's 2F. Was the other one 2F? 2F032C, and then this one is 42F032C. So this one that's the same status message again, assuming it's a status. It seems to give pretty much the same response as well. Is it the same response? Let's see it like that. VS Code doesn't highlight stuff that's this far away, which is kind of annoying. What I might do now is just copy it down, and here, let's just dump it here for a second just to compare it. So that's all the same. Okay, so that whole request response here on so starting at 33, that's all the same. So both the thing we send and the thing we get back is the same. So maybe that's like, I don't know, maybe something changes here. And then 35 and 36 are something else. There's kind of a second thing. So so what is that? 33, 34, status again, and then 35 to 36 is kind of another or different status, question mark. So it's not exactly clear what these things are, but that's kind of the breakdown of this whole exchange for going into a profile. Maybe the manufacturer is using some kind of library protocol and there's a lot of unused data. It's very possible. I mean, there's a lot of unused data in these exchanges just because it's configured. Like, the device has to configure with the host what the size of the USB packets are going to be that go back and forward. And you can have different sizes. I think... So this is a USB high-speed device, or a USB 2 kind of device, and the maximum size you can have in an interrupt, I think, is 64 bytes. But I don't know if it's like it has to be 64 bytes. So it could be the case that it has to be a 64-byte packet, or that they're choosing to use a 64-byte packet because they have some exchanges where they want to send that much information. And because of that, like, smaller exchanges are going to have like way less data. They're not going to use all of it. That would be my guess in that case. All right, let's take a look at the second one and just see how different or similar it is to the first. So So the second one starts at 30 set. Well, it actually doesn't start at this. I'm just going to cut these keys out because they're not really useful to us. And also, let's just make some space here so we can see that this is the first part. So 45, 04 to F, 003 to C. That's the same as far as I can tell. Let's actually grab the response that we get and see if it is the same response again, because it looks similar. What we're really looking for here is like 1 byte to be different, 1 or 2 bytes to be different, because that 1 or 2 bytes somewhere should encode the profile number. I think, right? We're changing profile. We're telling the keyboard we're going to a new profile, so we would expect that somewhere in this there's going to be something that says this is profile 2 or this is profile 1. So these look the same so far. Oh, something's different here. All right, so here's already 1 byte that's different. This one's 2. So, oh wait, this is the. I'm getting myself confused here. Yeah, this is the one. This is the original, and this is the one. So this is actually going to profile 2, and this one was going to profile 3. This one's going to profile 2. I guess there could be some information about here, maybe about where you've come from. So which profile you were in before. So previously we were in profile 1 and we went to profile 3. But okay, so in this case there is a byte difference. There's a byte difference here on 2, and then it looks like everything else is the same. Is that right? Everything else is the same, and then all of that is the same, and then the next part is the same. So there's a difference, this 2. So I'm just going to make a mark there to show that that's where a difference comes in. That could be the profile number. And actually, let's maybe just go and have a look already at the third profile, or setting profile 1, which is at 81. So let's go to 81. Let's copy this response as well. Go down to 81, and C begins at 81. So let's put some small gap there. All right, so yeah, so that one is 1. So let me get this straight, because I'm now getting confused. First we went to profile 3, then we went to profile 2, and then we're going to profile 1 at the end. So here, this one sets 1. The previous one set 2, but I think the first one set 0, which is kind of weird, but I guess it's possible. Yeah, the first one has 0 in this place. The second one has 2. And then the third one has 1. That's kind of strange, but all right. It's not like I mean, there is 3 distinct things there, so that's kind of useful. My guess is that is the current profile 0 based. Oh yeah, I guess that would make sense, right? This is kind of where you're at. So we started on profile 0, and then we went to profile 3. And then we get, yeah, I think that actually makes perfect sense, Maximo. Nice observation. I'm just looking here. IQW says, hello, I have a question. You seem to know a lot. I bought my mouse 1 week ago. It starts to disconnect and reconnect out of nowhere. I followed every video and nothing seems to help. You could definitely try this approach. I don't know if this is the best approach for debugging that kind of mouse problem, but I mean, you probably learn a lot about how that mouse works by doing this. So this could be a way of doing it. It's gonna do a water refill. All right, so okay, yeah, so that's actually that actually makes a lot of sense. So that first profile is like status about current profile, probably. Then when we did status again, yeah, so this 33, maybe I was wrong. I mean, I thought that I actually checked the response there. When we do 31, not 31, what is it, 33? Did this, and then that byte is 0 still, right? Zero, 1, 0, 8, yeah. So the status thing we do at the end is still the same. Okay. So what else? Then we go into these other packets. So we begin the transaction. So we send then this. Let's see what we're sending second time around. We start the transaction and we send that. Is this the same? That's actually all the same. And is the response the same? Because we get some extra information there as well. That's what we sent. And we get back something that seems pretty much the same. That's the same. That's all the same. Yeah. So that might be preload. It could also be that these profiles just have the same settings. As I mentioned, right, I haven't changed the settings, so it's very possible that the settings are just the same, and we're going to miss some stuff because of that. But all right, something in here is going to be like the identifier. All right, so then let's grab the next thing that gets exchanged. So 3D. So then we do this one, and that's that one. Then we're sending this, and these are the same. And it looks like everything else is 0, so that is pretty much the same. Nothing changing there. I mean, it's not strange, right? It's not strange to see packets going back and forth that are like the same data for these things, like in this big exchange. That's also kind of expected. If you think about how you would kind of write code for one of these devices, you're probably going to have some common functions, and like you know, you're not always optimizing for like the perfect communication flow or something. Sometimes you just reuse some code. Maybe it sends a couple of packets back and forth that don't really need to be exchanged. Also don't know it yet, so but that could be the case as to why we see some stuff like that. Why don't I copy both of these at this point? And we'll take a look at both at the same time. So that's going to be here. So first one, that's all the same. Everything else is zeros. So anything different in the response, that's all the same. That's all the same. That's all the same. So nothing in that packet, and then that's the end of this first exchange. So I presume that there's nothing really happening there. Could you use a diff tool to quickly spot the difference? Might be something to add to your hex viewer tool. I was thinking the exact same thing. Yeah, it's possible. I could open this file side by side and kind of look at it like that, but I find like the easiest way, well, maybe it's just me, but I find the easiest way is to just put it there, and like the quickest way to spot the byte differences is going to be like just scanning it out and seeing it. Maybe that is not the best way, but we'll see. So that's the end of that exchange. That seems to not have any particular specific meaning in it. And then it's the beginning of another one. So let's grab these two packets, drag them down here, end of the exchange, the beginning of the next exchange. Now I'm gonna be like self-conscious about copying these packets, and I'm gonna accidentally click Control-C a couple of times. Alright, where are we? So it should be here. No, it's the end of the exchange. Where am I at? Alright, so this one... Hang on, what am I doing here? Here it is. Alright, so this... I wish that it would do, like, allow you to go over multiple lines, though, and just compare these packets. Alright, so that one is the same, right? There's nothing... Wait. No, it's not the same. Okay, so maybe this is the beginning of seeing something different here, because I see 4.9 and then 4b. And this would be saying... this one would be saying go to profile 3. This one would be saying go to profile 2. So there is a difference of 2 between these, which is strange, but okay. Are there any other bytes involved? So that one's 49. Oh, interesting. Okay, so this byte is also different. So this one is a 2, and this one is a 4. So we've got 4b and 4. And then here we have 4, 9, and 2, so a difference of 2 between both of those. That's pretty interesting. So I think packet 59 or 15, let's just mark it in this initial one. So I think 15, which byte are we looking at there as well? So that's byte 1, 2, 3, 4, 5, and 6. I think bytes 1 and 6 contain profile. Somehow, if we see a difference of 2 in the other one as well, then that's going to be a really big indicator. So let's grab that. Let's check down here. It's the beginning of this exchange, end of the exchange, beginning. And yeah, it looks like it, because I see excuse me, I see 47 in there. And then where's the 2? Here, 0, 0. So there is a, for some reason, I don't know why, this one has 3 different numbers, but there is a difference of 2 between them. It also does seem that that is the addition of these two, right? 11 plus 36 is 47. And in this case, well, in this case, that's not, no, that breaks at this point. Wait, is that true? Because that's 11 plus 36 plus 2 is 49. Yeah, okay. So maybe this, maybe what it is this is the part that actually encodes this thing, and then that is just the checksum for the whole thing. Interesting. But it is kind of strange that for whatever reason we're encoding the profile as 0, 2, and 4 rather than 0, 1, 1, 2, which I would have expected. But still, that's great, because that actually looks like that is probably the pattern. We can try it out and see what happens. Okay, so then maybe I should split these up a bit as well, so it's easier to jump around. So that was in request 1. No, 15, so that's actually not in there, that should be in here. Just catching up in the chat. Seeing if there's some way that I can optimize this experience. I'm thinking maybe just to open 2 files side by side, and then I can at least have like 2 streams, but I think it's just like takes up just a little bit too much space. Still, maybe it's a better way of doing it. It's not quite a proper diff, but it should help a bit. Okay, so that was packet 15. Then we get a response, which is not providing any information. Then we have packet 17. So then that is going to be... Where does this one... no, I'm going too far. What I really want now is like to just record these as offsets and to be able to jump to this thing and say, oh, I go to this offset. Like packet offset. Okay, so that's the end of the exchange. That's the beginning of this one. So this is where we are encoding that byte. And then I just want to see the difference with this next one. So that's going to be here. And what do we see? There is some difference, and also there's some differences of 2. So I see 0477, and then this one's 75, 0A, and yeah, again, so it looks like we're encoding that. Same like two stride index here. There's a bunch of random zeros and FFs in there for some reason, but okay. I think we've cracked the profile encoding at this point. There's still obviously the mystery of what all of these, like what every other byte in this whole exchange means, but I'm content to not like discover all of the mysteries today. At least about the profiles. I think it's nice just to get the functionality in and basically like do something really dumb, like, you know, just send all of these packets in sequence. You know, like if we know that these are the only things that change, right? Like if we know that like this has some base, right? If it's a checksum, that's the reason we can use these bases as well, right? We can just say that profile 1 has base XYZ. For these different exchanges, and then just all of these other bytes change, but we've kind of got like a prototype. Elsie says, what kind of drink is it? It's water. The purest of drinks. All right. Yeah, so I think just sending this data is going to work. Yeah, what I wanted to do is I wanted to find in the 3rd packet, and this is the 3rd packet, like it's the start, it's the end, start, the 47, and then this one, 73. So we had 77, 75, 73. So this one is also following that same format. And then here I see B4. And here I see B0, which also makes sense. It's the same offset thing here. Here we have a 4, here we have a 0. So like, it seems that there's a bunch of information being exchanged. I'm not sure what these packets do, like what they're actually identifying. But certainly that pattern is there. And we should be able to just like ritualistically play it back to the device, and it should hopefully work. Alright, so that was, what do we get here? That's B and B4. So then we get this packet here, EB, here we have E7, so presumably we have the same offset going on again. EB, E7, E7, then we get 1F, 1F, and we get 23, so yeah, that's the same difference again, right, from 23 down to 1F. And then at this point, 5A, 5.6. Seems about right, but this one we have 5, and here we have 1. So there's still a difference of 4, but now we've got some different offsets. Yeah, so all of this information, like whatever is being exchanged here, is just setting this stuff up, like for this profile. And we looked at this different status thing, so that starts at 35. So if I go down here, just jump to 35, because all of this other stuff looks like we're seeing what's going on there. I'm curious about what we see for these last two packets. So that one's E4, and this one's E3. That's quite interesting. So there we have a difference of 1. Well, here we're sending. Oh, it looks to me like we're sending this information that it sent us in the beginning. Like we send that to the device again. That's interesting. And presumably, yeah. Yeah, I wonder if this is just like, this is like some sort of sanity check that the device does. Like here's a bunch of data. Exchange some data with me, and then at the end kind of confirm the whole thing by sending me back my original message. I'm not sure. But is that the only byte that's different? The only thing about having these things is now I can't like easily scan it like this. So 0, 4, and we get a difference here of 1, which makes sense. And this is 0, 3, 4, 2C. Yeah, the rest is all the same, I think. Looks to be. Yeah. All right. So I think at this point, let's zip over to the main code and see if we can just like implement something and see if we can switch some profiles on the thing. And probably we can start to abstract some of this stuff away. Like, I think it might just make sense to, like, for example, just have some buffers around that, like, encode, like, the header and the footer and stuff, so that we don't have to constantly, what do I mean to say here? Yeah, constantly, like, construct them again and again and again. So let's call this one header buff buffer.alloc 64, and then we can just set that. It would be really nice to just be able to set those first elements. Can you do that with alloc fill? No, because you can only provide one value to fill it with. Oh, no worries. So let's do it like this. So this sets up the header buffer that we can just use and send all the time. This one will be the footer buff, and then we'll send 2s. We can go in and just replace like these parts. So we'll just send the header buff here. And we're receiving into the RX buffer, and I can already see, like, maybe not in these ones, but we're going to have to, like, be a bit more conscious about keeping that receive buffer a little bit clean, because some of the responsives we actually need to keep a hold of. Sending the footer. Wait, what was that? RX buffer. We're reallocating the RX buffer each time. Yeah, maybe we actually want to keep that around. Like clean it up each time when we need to. Okay, so that is, yeah, I think that's improving things a little bit. The footer in that case, header, the actual request. We'll do that at the end. Do that at the end. We want to send that. Footer buff. Cool. All right. So yeah. Let's see if we can get into a different profile. So we're going to have async set profile. And for all of these things, for like the levels and the modes and the brightness, like all of that kind of stuff, eventually I want to make like nice types for them, or enums, or like just fixed value type. But for now, I'm just going to treat everything as a number to keep it nice and straightforward. So this is going to be the profile. It's going to be a number. Promise of void. Let's just copy the previous one here. So in the beginning of a set profile, we don't actually just send these transactions anymore. Like this is the prelude. Like this is kind of us requesting some kind of state. RX buff, not transfer buff. All right, I made a mistake somewhere. Transfer buff. Oh yeah, that's right. Yeah, we don't need to empty the transfer buffer out anymore. True. Did I do that in the other one as well? No, in that one I did RX buffer. Okay. And let's change it here before I forget as well. All right, so we actually need to send this. This seemed to be the same in each case, so we send this, and we need to actually keep track of this data. So we're going to need to save this packet. So this is not just going to be a regular. It's not just going to be a regular RX packet that we kind of overwrite each time because we're using the same receive buffer. This time we're going to want to keep it around. Just catching up with the comments quickly. I don't know anything about low level, and I only know a little bit of JS, but it's not enough. Keep doing videos like this, and I'm sure I'll back and watch all the videos when I get enough experience. Yeah, I mean, they'll always be there, so you can always come back. I think that's a really good pattern to get into anyway, in any case, right? If you see something that is a bit out of your reach at some moment, make a note of it, put it in a bookmark or something, and come back later. You know, however long that ends up being, a couple of months, 6 months, a year later, come back, and what you'll often find, at least what I find for myself, is that I often I come back and I'm like, wow, I can't believe how much more I understand from this than I did a year ago. This is like, it's a really satisfying feeling. You don't see that on the day-by-day growth, but you do see it when you come back after a year. Greg says, is there a way to pack the buffers more concisely? Yeah, probably if probably we could write some utilities around it. Like I was already thinking, it would be nice to say allocate a buffer of this size and then insert these elements into it. And I might do that actually, because I was already getting a little bit annoyed by it in this case. So let's do that. Let's make we've got this utils file that Greg already made. So let's make export const alloc and set. So we're going to have a number of bytes. Let's call that num bytes, and then we're going to have initial values, and that will just make that an array of numbers, because there's no point in like making that more complicated of a type. And then we can create a buffer. So I'm not going to do any checks here for like making sure that number of bytes is greater than 0 or anything like that, because I'm just going to trust that this is an internal API that gets used properly. And then we can just iterate through those values. And we can set at that index the value. And then we return buffer. Yeah, so I think that's a nice, slightly more useful way. All right, let me go and use that utility now. So let's import from utils alloc and set. And then here we can actually just use that instead, alloc and set, and then, oh no, that's, and then here we'll cool. I'm already way happier with that. Thanks, Greg. Yeah, sometimes you just need that little push to actually spend the time to write the little tool that you need to solve the problem that you're facing. So that's actually a much nicer way of doing it, and is basically doing exactly what we need to do each time anyway. I might as well go and refactor these parts as well now. It also makes it like once you have that, it makes it such like we don't have to worry about like making lots of buffers. Like we're not like short on space here, so we can create as many little 64-byte buffers as we want. There's sort of no thing there. So it also makes it way easier to just think, okay, we'll just make a transfer buffer at this point. And we don't need to kind of alloc it up there. We can just say const transfer buffer equals alloc and set 64. I'm still kind of interested to know what happens if what am I trying to do here? If you don't like allocate a 64-byte buffer, I think that libUSB, or sorry, node USB in this case, would actually just like fill out the buffer for you, because it knows that it has to be 64 bytes. But I think we'll just do it properly and allocate 64 bytes at a time anyway. Cool. That's already much nicer as well, I think. Like you can just have them in line. You just create the transfer buffer. I'll leave this like that for now. Let me do that. Fine. Get rid of transfer buffer again. Do the same thing. Const transfer buffer equals alloc and set 64. And we can do cool. And yeah, we're in set profile actually. Oh, well, it's fine. It is fine. I can actually just copy that in here. And get rid of that. And we have mode. Yep, cool. That's all good. So, yeah. So what I want to do is I want to... Yeah, I can just do it in line here. Now we've got this utility. So we're not doing like we need to kind of do this like prelude step, or what we were calling like status. I don't know. Status request. So we're going to do a command transfer, alloc and set 64, and we're going to send this byte sequence. And this, everything else is 0, so let's do like this. Alright, so we're going to send that, and then we are going to want to get like a receive buffer that is, well, let's just do it in line here. So it's not going to be something we overwrite. This is going to be the like status response. Allocate 64, and then we will do an interrupt transfer where we write into that buffer. So then we get that, and so we do that, and then we begin the actual transaction. So that's kind of just what we've been doing. Let's close that old file now. So keyboard log. So that was just the old part. No. So we're going to have a lot of these transfer buffers. So what do we do first? Like we... Oh wait, this is what I'm getting wrong. The header comes after this exchange. I've been using some different IDEs lately, and there are some keyboard shortcuts in those that are really similar to VS Code, but are like very slightly different. Like for like doing indent and unindent, and they do quite different things, and it's really annoying. The other one is an Eclipse-based IDE. I don't know if that like triggers any you know, bad experiences in people. But yeah, I'm not a big fan of these Eclipse-based IDEs. I really wish that everyone just built everything around VS Code these days, but I'm not sure that will ever really happen. Okay, so in this first request, this first part, we saw it changing down here. So that was, oh no, so that initial request actually does contain some specific information indeed. So it was 2F032C, and then here it's 42F. Wait, where is the difference? Is it just in the response? Because this is the response about the current profile, right? So this is the, yeah. So let's call this current profile response. But yeah, I think when we send, what we end up sending back is not this exact thing anyway, so it doesn't matter. We only need like what is it, we want the bytes from here, so we want everything from byte 8 onwards in that case. So I don't think it makes a big difference in that one. This first request didn't have any difference, I remember. But it does have quite a few bytes, so let's kind of clean that up a little bit. Alright, and then we can just take every space and turn it into a comma. that would be a nice place for a macro. Alright, so here I think we don't need alloc and set because we're going to send all 64, so let's just do buffer.from in this case is better. Buffer.from. Yeah, so we're sending this, and this was a this part was standard, so this is going to be const profile transfer common. Yeah, I'm going to give these better names at some point, but we'll just have it like that for now. Since this one is common. Actually, you know what? Like, it's fine for it to be inline. There's no special... It's not going to be shared with anything else, probably. So that's fine. So we're going to exchange it. We're going to put that in the generic RX buffer for now. And clear out the buffer. I think we don't need to keep clearing out the RX buffer because we're not doing anything with it. Like, and when we are doing something with it, we're kind of putting it in a special thing. So we just need some scratch, basically. So that's that. We write into the RX buffer. Actually, we don't even get a response, right? We don't even do this command. We do a command transfer, but we don't do an interrupt transfer yet. So we can actually just get rid of that for now. Alright, then... Wait, no, that's not true. We do an interrupt transfer after that. Yeah, we get something back from that. No. What am I saying? Okay. It's always symmetrical. Well, so if you have a question, you can just throw it into the chat. It's the easiest way. Max, Eclipse is not that fun, but more fun than NetBeans. I haven't used NetBeans, I'm afraid, but yeah, I remember seeing it many years ago, just around. So I've been lucky enough to avoid it. I've actually never really written any Java. I've written like, I don't know, a couple of lines of it here and there. I've read some Java, but I've never actually really needed to write Java. I'm using an Eclipse based IDE, which is for like STM32 microcontrollers, so it's like C and C++, but it's like they've got a whole custom GUI interface thing for configuring the chip and like assigning all the pins and everything, so it's like it's really useful in that respect. But I know that you actually can use this, like easily program these tools using things like make, and you can just use that tool for the pin assignments and things like that, because it is actually really useful for that. But yeah, that's what I'm using it for. Dream Deck Up says, hey man, just wanted to say that I'm enjoying your content, especially the RISC-V stuff. Keep it up. Oh, thanks. I will get back to the RISC-V things. Like, the RISC-V is not, people have asked, it's not stalled. Well, it's stalled, but it's not, I haven't given up on it. It's just there's only a finite amount of time in the world to do things, and I will get back to it at some point. Yeah. Max mentions that Java is by far his least favorite to write, and it was all over his college courses and never again. Yeah, it does seem to be like still for some reason a really popular teaching language. I'm not really sure why. Like, it doesn't seem like there's nothing wrong with it, like, intrinsically, but it's like, I don't know, why would you teach this language at this point? Is it I think it's just inertia. Like, all these schools have courses already made and books and, you know, all of this kind of like industrial complex behind the education system, which is just like moving Java along. I don't think it's like a particularly good language to teach people. It's not a bad language, but it's just not, I don't see anything particularly special about it. Back to the packets. Alright, so that was the response to that one. Then we send this one. This one, I should have made marks here. This is packet 9. Here we got some kind of difference. We send this 3D thing. This actually seems quite different. Did I check that before? Because that seems quite a different... Oh no, I'm just on the wrong thing. So this is the one we're sending next. And let's double check that that is kind of also 3D. Yeah, it's highlighted, so this is the thing we can expect, and we get some bytes in response there, but I don't think we need to use them, so I'm just going to throw them away. Alright, so what are we doing here? We're getting, we're going to do a command transfer. I think I'm just going to like inline this. I think I'm just going to inline all of these. Well, in this case, this one is an alloc and set. 64 bytes, and we only need to send a few specific ones there. And then we need the interrupt transfer afterwards. And then this one, I think I also don't really need to pull it out and give it a name. I can just send it. I'm just catching up on the Java discussion that's now going on. Java is great for teaching because it's verbose about things under the hood. And Max says, I think the verbosity gets in the way of highlighting core concepts though. I've been studying and get lost in the syntax. But it's less finicky than C without some of the abstractions of Python. Yeah, I mean, there's one thing you can say about Java is that it has like, it's got a lot of stuff going on. Like you have to tell it tons of stuff. You have to put all kinds of keywords all over the place and like really get these super object oriented concepts like burned into your brain. Like this is my, you know, abstract, well, I mean, there's nothing wrong with things like these actual concepts, but like Java really puts a lot of them around. And they're nice concepts, but it really seems that it needs to, you need to use them all the time, even if you don't understand what they're there for. Yeah, I actually think people should just teach people Python. Like, I think like university should just teach Python for the most part. And if you want to like, you know, get people into it in that way, and then if you want them to understand something more complex or do something more like computer sciencey, get them to then write a Python module in C. So then they're forced to go into C, but it still relates back to what they've been doing in Python. I think Python is probably like the least, that's like just the easiest language to get into. Like I love JavaScript, and I also think that's a really good language to teach people. But yeah, I mean, just for the like sheer ease of how quickly you can get into stuff, I think Python is a really nice language for that. All right. So that was that packet. If we're gonna get anywhere today, I really should actually write some of this code. And then we get to this one. This was 91, and I'm fairly certain that this one did have some differences. So let's go up here. So 3D, 67, 91, maybe not. Maybe this one was the same. Wasn't this whole middle transaction was all basically the same, right? I think. So, oh, we don't need those 0 bytes. So I'm going to do these ones again. Cool, that's that packet. So this is like kind of transaction 1, 91, and that's the end. So then we have an end of transaction. So the footer. So this is, yeah, this whole thing is transaction 1. And then we can kind of just ignore the header and footer part because they're not particularly special to the whole thing. Then we get to transaction 2. So we need another header and another footer. So Max says, I had a job teaching Python to literal children for a while, and they got it just fine. Yeah, it's like writing sentences. If you can write sentences that are like kind of instructive, then you can basically already write Python. So yeah, it's super cool for that. I can see why like so much of the world has built its tooling around it and that kind of stuff. Also Ebpf, which we'll see in a bit if we manage to get into that. The Ebpf tooling is all, like, a lot of it is based around Python and Go as well. Cool, so we're beginning the second transaction, and that is here, close, open, this one, and then this is the beginning of kind of our having an actual offset to the mode. So this is packet 15. So around packet 60 is where we would expect to see that. Yep. So that was, let's just get the exact relationship between these things. So that's mode 3 is 4B, and then 2 is 4.9. So yeah, 4.7 is the base in that way. Let's just cut this whole thing, take it back. So 4.7 is the base. For this one piece of code. And we only need a few bytes here, so we can do an alloc and set again. And there really should be an easier way to do this. All right, so let's here. So we got this. And at this point, that's going to be 4.7 plus. Let's maybe just make something at the top, which is, oh, well, this actual request thing is, oh, that's LED mode. Yeah, let's make a profile, like profile 2, which is just profile multiplied by 2, because we have this 2 offset. So that's going to be profile 2, and presumably then that 4 is our offset, because that's going to be, the profile is going to be 2, so that's also going to be profile 2. Cool. Yeah, and we could make this some checksum, but this is the easiest way to do it. Okay, that's nice. And then the rest is basically going to look like that, I think. So we have that 49, we have this one. We have to send a bit more data here, and there might be some actual meaning to this when it comes to other stuff, like to do with the key mappings and that kind of stuff. Like, I'm not sure what all of this is, or what these Fs mean, or any of that stuff right now. Maybe it means nothing. Maybe it's, I don't know. It probably doesn't mean nothing, but oh, I see that there is like some really intense Java discussion going on. I'm going to come back and read this later, but I'm not going to get into it now, otherwise I won't finish this. The thing about Java is, for OOP, is that it's such a wild divergence from the original ideas of OOP. From this like outside perspective of someone that doesn't write Java but has written it and had to like has read it and had to evaluate like older products that were written in Java that needed to be like remade for whatever reason, often because the team that made them was no longer around. It just seems like this language that is like, it's just around for like people to like write thousands and thousands of lines of code of abstractions that don't really do anything or mean anything. Like don't help in any way, but yeah, it's like fueled by this like 90s era obsession with OOP. I think there's a lot of that in it. I think it really got influenced by that whole thing. So what Nate is mentioning there about this, like, it being part of this big hype, I think there is a lot of that to it. Okay. So we're going to send another one. And in this one, this is 7.5, right? And we're going from this, so it's going to be, what's that, 7.3 and then 7.1, so 7.1 will be the base in this case. Again, we could just add these other bytes up, but where is the fun in that? Wait, actually, where is the, do we have a 4 in here, or am I copying this from the wrong place? That's very possible. Yeah, I'm like copying it from up here, so the easiest place to do it would be from down here, because this is the base. So here we have 4.7, here we have 7.3, yeah. Let's actually take it from here instead. Alright, so 7.3 is the base. And the only problem with doing it that way is that now I can't see which byte holds the offset, and not the offset, but the kind of the actual value. So 4B77, and it's byte 6. So here on byte 6, that is that one. So 0, 1, 2, 3, 4, 5, 6. Okay, so this is in the same place here. I think with this one, it's easy. It's going to be easier to just do like an actual buffer. So buffer.from, and let's do it like this. It's not quite going to line up. So let's just type this in manually. OA 11 36. Then this one is also 36 apparently. Then we get the profile 0 0 0 0, and then let's take the rest there. Cool. Alright, and the rest of these things, at least only this second line change. It's fine. You can just do it like this. And then we'll get a few lines of zeros. Like that. And then we're basically going to have Alright, cool. It's kind of ugly, these like profile 2s in there. Maybe it would be good to make this like 4 characters long, so it like more or less lines up with this, but I'm just gonna leave it for now. There is a... Do you actually call release? Calling release is actually one of the things that Greg set up, I think. Maybe... Yeah, so what you can see is that in the main code of the driver, there's a try catch finally, and yeah, Greg set up calling driver release in the finally, so that's really nice. I think it's also what we should also do is register a like a signal handler for if the program gets like control seed or if it gets killed for some reason from the outside, so that we can just very like as fast as possible just try to make a call to release, to try and release the driver. But it doesn't make a big difference if we don't like release it back to the kernel. It doesn't seem to, like, since the kernel doesn't have a driver that deals with this part, it doesn't actually make a difference anyway. Like, it's registered as a mouse and the kernel picks it up as a mouse and says, okay, I'll try and do mouse things with this. But there's no mouse activity coming from it, so it doesn't actually matter if we release it back to the kernel or not, but it's good to be sort of a good citizen and sort of, you know, leave the world in the way you found it, if that makes sense. Hello, Code Man. Why are you in my recommended? I don't know. I get maybe because you like code. Maybe that could be. So cool. So this packet. Let's see where we are. We've on to the next packet, and that was the 7 packet. Here we have B4. How many more do we have here? Quite a few. So this one, B4, and let's just check out what the base is. Yeah, the base is B0. Cool, and presumably the thing is in the same place. And yeah, apparently there's F's all the way down here, so we'll set those up as well. So B0 was the base, and then we're doing 3, 11, 36, 36. Wait, no, 3, 11, 36, 6C. 0, 4, which is the profile, and then here there's a bunch of stuff going on. So 3 zeros, then an F, and then the rest are zeros on this line. Wait, something's wrong here because we have too many things. Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Somehow we ended up with 17 bytes on this line, which isn't right. So we need to go back to the previous thing. First, what happened here? So we get the 36, then we get the place with the profile, and then here there are 4 zeros in a row. So 1, 2, 3, 4, and then there's an extra 0 here. Okay. So 1, 2, 3. So I'm not yeah, maybe it's actually better not to start off with that one. So see profile 2, 6C, 4, which is profile 2, then we have 0, then 3 zeros, 1, 2, 3, then there is an FF, then there is 4 sets of zeros, so 1, 2, 3, 4, yeah, so you can just get rid of that one. And make those 0 zeros. All right, so then on the second line, like it looks like everything is a 0 except here on this FF. So let's do this, and that's byte 2. And then there's just a whole line of zeros, and then there's a whole line of zeros, but the 5th byte back is an F. 1, 2, 3, 4, 5. Again, I'm sure this is encoding some sort of real meaning, but it's not clear what it is here. So that was these. Where are we up to? That was the B one, so we're on E now. And so E7 is the base, presumably. So we have B4 and then EB. So E7 is the base. I really need a better way of doing this, because it takes seemingly ages to do this. But that is kind of part of it. Alright, so E7 profile 2, 11, 36, E2, and then that's profile, and then we have 0, and then FF 0, 0, 0, 0, FF, and then the rest is that. So that's kind of common, and then everything else is zeros. Oh, okay, everything else is zeros, which means we could do this as an Alec set instead. Yeah, something like that. All right, and then so we had these E7, then we get 1F, and let's figure out where that puts us. Yeah, okay, so that's that goes up to 23. And again, this one actually only has a few things, so we can do again an Alec set, which is nice always. Yeah, so let's just type it manually. So 4, 1F, profile 2, and then this one is a 1, 11, 36, D8, D8, profile 2, and that's it. Yeah. It even kind of acceptably fits on one line. All right. This is, I'm not sure if we're going to get to the other goals of the key assignment. Well, it's okay. We can do a few reverse engineering streams. I might do some stuff in the meantime and kind of do an update, because this is quite this is basically the work. This is what you do in the reverse engineering. It's not actually the most glamorous thing in the world, but it is really fun. And I think if you've got a lot more of a complicated device, like there are some other USB devices that I have that only have Windows only drivers. One of them is my oscilloscope, which you can't see, but it's up there on my sitting up on my desk. And that has a mode where you can actually get basically a full USB readout on the computer, but only in Windows. So I would like to actually try and reverse engineer that at some point as well. Tanabaya says, I'm sorry, but what? How can you do this in JavaScript? I've been a dev for a few years and never knew that. Wow, that's really awesome. Yeah, you can Google Node USB and libUSB. And you can see, yeah, basically you can interact with USB devices directly with JavaScript and basically any programming language, actually. Yeah, and that's a way basically you can communicate with the USB device. Yeah, you should have write a utility function that converts the package log data into a code string. Do you mean like this data? Actually, it would be relatively possible to do that, and maybe not even the worst thing in the world. But I think the fact that we would need to replace these bytes would make it just a little bit too annoying. So 1F, I'm trying to remember, is that the one we just did? Yes, it is. So we need to do 4, 5, 6. And again, this one only has a few bytes. Perfect. And this is not the base. So this is... Oh, this is the base. So 5, 6. 5, 6. Oh, this might be the one where this is like off by 1. So that's 5, 6. And then we go up here. And then 5A. Yeah, this is the one where it's like, it's offset by 1. Which is good to know. So the base is 5, 6. And here it's like 1 plus profile 2. And the rest of the bytes. So 5, 6, 0, 0, 1, 1, 3, 6, 0E. Then 1, then 0. So nice. That is that. Are we drawing to the end here with this one? Yes, there's just 2 more. So this one only has a few bytes, so I'll just copy it from here. It's got an offset of 90. That has 5 again. Are we on the first? So this is probably the same as the previous one. Oh no, I'm just looking in the wrong place. Yeah, I think this has the same like 1 offset thing going on. So 0, 4, 90, profile 2, 0, 0, 1, 1, 3, 6, 4, 4, and 0, 5, and then that's it. So that's that one, and then 1 more. And again, it's just a few bytes. So it's going to be C6, 0, 0, 1, 1, 3, 6, 7A. And then, yes. So that's that. Then we send the footer, and then this is the part where we need to like echo back that like packet that it sent us in the beginning. So we're going to send... Wait, no, we don't even need to send that back. Am I just thinking wrongly about this whole thing now? Or there's an exchange of a couple of packets. So, you know what it probably is? It's probably not even that first one. I think what we do is we just... Oh, this was a copy of that same request again, right? So we send this request, we get this response, which it looks... Is it the same? No, it does differ in this... Oh yeah, it differed in this byte. And we need to update it. Yeah, okay. So we just do this exchange again, and then we send this back with a couple of updated bits and pieces. Alright, cool, we're getting there. So we send... What is it? This one? And this is the final transaction. So we're gonna we're going to send this, and then we're going to send like we can just edit, like basically edit our original buffer, because we only need to, like, we can edit this current profile response buffer. I think that's going to be the best way to do it. So the current profile response, let's think about how is a relatively nice way of doing this. So we're going to take these bytes, and I'm presuming that byte 6 is probably also still going to hold something. Oh no, this is the first packet. So maybe here it just didn't hold something, and then later on it does. So 2F. 2F. Now I'm looking at this one. So 04. Yeah, okay, so there's already something different in here. So maybe, yeah, I might get this part wrong. It might be that we need to send something to do with the, like, we might need to send like the current profile plus we might need to send the current profile and then like the thing we're updating to. In this case, we're going to profile 0, basically. And I think it's like differing in this one. Again, let me grab the, like, this final thing here. To F to I'm getting lost. All right. Wait, this looks to be. Oh wait, where should I be looking? 35. Yeah. So it differs here in this byte, and then it differs again on the second row. Yeah. So yeah, I think we need to be like stating where we currently are. Does that make sense? Yeah, so then this is E4. The E4 is like the E4 is probably offset by the current profile of wherever we are. So I should check actually this first one. Yeah, so E2 is probably the base in that case. Because, wait, or is this where we're going to? Because we were, like, this is, so E4, from here we're coming from profile 2. I'm confused. We went to profile 3, then profile 2, then profile 1. So we're not coming from profile 3 at this point, we're coming from profile 2. So, and at that point we were in profile 1. So maybe this is check the chat to see if anyone has noticed that I'm doing something stupid. So like this byte here 2, here we're going to 0, so that makes sense. And at this one we were going to, oh okay, so this one is like a 1 indexed thing, like not this multiple of 2, but this is just like a, and so the rest looks to be the same. Now I just need to figure out what's going on. So the first one we're sending E4, and the second one we're sending E3. Ah, it's one indexed again, and it is where we're going to in that case. So in this case, E2 is the base. E2 is the base, and this is like, this is 1. This one should be 2, right? No, it actually still sends a 1 there. Does that make sense? Huh? That one sends a 1. Oh, they're both sending a 1 in that position, and it's, where is it changing? It's changing on this. Oh, it's in this position. Okay, so this one is the third byte. Okay, so in this one, the third byte is a 2 because we're going to profile 2, like from a 0 index perspective. In this one, the third byte is 1 because we're going there from a 0 index perspective, and there it should be just 0. Yes, it is. Okay, so all right, I've got some idea of what we should be doing now. Maybe we can actually just send this data, like, and not even worry about that initial thing. We'll see if that works. Stuff might break later on when we get to other parts. Like, if this really does encode some sort of profile status, then this might break if we change something in the profile later. Okay, so I think we'll just do a like copy from. No, it just makes sense to do it straight from here. Oh, yeah. Oh, sometimes this just doesn't work the way I expect it to. Getting completely messed up here. Let's just do it like this. Yeah. Cool, alright, so that is the basis of the data. And we want to do, like, wrap it in this. Missing a comma there. And we want to finish it off with that. And then, okay, so the E2 is a base which is offset by just the profile. And then in the second row, the third byte was the profile. So the second row, this one, was the profile. Okay, so if all works correctly, like, this should set the profile. Just catching up chat. Francis, would it be easier to just capture and replay the packets? Trying to decode this protocol without any documentation seems pretty difficult. Yeah, it's pretty difficult. I mean, that's more or less what we're doing, right? Basically just replaying the packets back to to the thing. But like, I think it's I think it would be really unsatisfying to at least for me to completely robotically send it back, because then I feel like we didn't reverse engineer, like we didn't get to like the same level of working driver. We just kind of, it's possible and it would work and it would make sense. But I think you can only go so far with that. I think like we wouldn't be able to apply that same thing, for example, to like key assignment and macros and that kind of thing. So this I mean, I'm kind of doing half. Like, I mean, like, I don't know what the rest of these bytes mean. Maybe they mean something. Like, we might get there eventually. But for now, we're basically parroting them back. And we're only changing the things that seem to do something. I think now is a good time to just test it out. Like, see if it works. And I'm sure that if it if it doesn't work, it's going to be, like, super annoying to debug. But, yeah, let's just try it out. So, what we can do here is we can leave the same test in place. Actually, why don't we see that the modes actually change? Let me just run this code to make sure it actually still works. So ts node source. Nope, does not look like it's working. So I do not see it working correctly. It's scanning through. I should check actually that it's actually in the profile mode, because maybe it's not. Let's just first go into Windows. Oh, it seems like Windows closed itself down. That's funny. Maybe I closed Windows down without realizing it. But I need to just boot that back up now. And while we're doing that, we can already pass the USB device through. Just need to check that it seems to me like the packet is the full config, number 35, I mean. Like the very last thing. Yeah, I mean this, I'm not sure what it can configure. It could be the case that it's configuring I'm just always clicking this annoying message that comes up like some file is not from some other piece of, oh, okay, so it was in profile 2. Or maybe you actually entered profile, no, that can't be right. So it could be the case easily that some of the stuff wasn't working just because I wasn't in profile 1. I actually have the idea that like setting the bright, and that's why I did this test earlier, setting the brightness and that kind of stuff, I'm pretty sure it's profile dependent. I'm not sure. I actually also just want to quickly check if this is profile dependent as well. It is. The USB refresh rate is profile dependent. We should cover this. This one should be really easy. It's just setting up 4 things. So we're in profile 0. It's in this custom mode. Let's go to that. Okay, so I'm gonna stop sharing the USB device there. I'm gonna go back to VS Code. And I'm not gonna loop through all of these. I just want to see if the brightness still works. Yeah, it seems to. Let me see if you can see that as well. So I'm gonna turn out these lights. I'm going to go to the keyboard cam and I'm going to run this, and it should go from like turning the lights completely off to slowly bringing it up in brightness, and I'm pretty sure you won't be able to see too much. Yeah, so it definitely, like, I can see that there are 4 distinct levels of brightness going through there. And now that seems to work correctly, let's try out. It's going to go through those brightness levels again, and now it should circulate through the modes. Okay, so this is not working. The first mode seemed to work. What happened there? LED mode, so 8 plus mode, and then mode. That's lead. Yeah. I'm not sure about that. I'm not sure what's going on there. But let's see, maybe that's not really what we should be focusing on for now. Let's see if we can get this, can get the driver to change mode. So set profile. Let's set the profile to 0 in the beginning, like profile 1. Shouldn't do anything, but maybe it will do something. So from my perspective here, and maybe I can just show you, when I run this code, it basically does this thing where it kind of turns on and off. That happens when you like change some sort of setting with the driver. So that seems to work. And I think a useful thing to do will be to go to Windows and forward the thing again. And then just see which profile we're in. So we're in profile 1. So, okay, that just makes sense, I think. That is not the world's most exciting result, but I think it's a good one to start with. So let's set to profile 1. I don't know if this is going to look different in profile 1, but I'm going to run it. So I ran it. Okay, nothing looks different here, but let's check in with Windows. So forward the driver, the USB device, gmmk, run. Hey, we're in profile 2. So that actually works. That's great. Awesome. We successfully went into profile 2. I want to try something. Let's see if I'm going to put this on. Like, this is some LED mode. Let's see if... Oh, wait. Before I go, let's put something different on for profile 3. So I'm going to go into profile 3, LED mode, and then let's make this one ping pong. So in profile 2, we've got this, like, this thing going on, and then in profile 1, I don't know, I've just got my normal thing on there, so the one that you've been seeing so far. So let's do USB, get rid of that, go back to here, and what I want to do is just add a delay in there. So we're going to go to profile 1, then we're going to go to profile 2, and then we'll go back to profile 0 at the end. And why those got indented like that. Oh, this is going to be really cool if this actually just works first time. Alright, so I'm going to make a slightly longer delay as well, because I think it will be easier to see as the keyboard comes on and off. Alright, so let's run it. Yes! Awesome! Do you guys see that? I really hope that you were able to see that. I think it was clear. Tell me I was actually... I think I didn't share the keyboard. I'm so sorry. Okay, let's try that one more time. Alright, now I'm sharing the keyboard. So, from my perspective, and I hope you can see this too, that actually just showed 3 different LED modes, and we're not changing the LED modes, we're just activating the different profiles. So, profile reverse engineering works. I'm really happy with that. And I think I'm going to have to call it a day here, even though I actually wanted to go quite a bit further with this today. But we'll see. I'm going to keep going with this. I'll probably do a little bit of work in between if I have the time. I'm just trying to watch back on the screen now if it actually... yeah, I think I missed it. Yeah, it works. I'm actually really, really happy with that. So, like, God knows what all of those packets that we're encoding here actually do and say to the keyboard. It would be really nice. One thing I might do, and I have a hard time to bring myself to do this because it doesn't quite fit with the theme of the channel. But one thing I would love to do is to try and dump the actual firmware that's running on the chip inside the keyboard, and maybe bring it up in like Ghidra and like see if we can actually track down the code and like disassemble it, and maybe see if we can see what's going on in the actual code, because that might give us some hint as to what is actually like what the meaning is in some of this stuff, without like what we're basically doing now is like a true like, I don't know if clean room reverse engineering is the right word for it, but like we're just like observing stuff, like observing a sort of side channel in some way. We're observing the channel, right? It's not a side channel, but we're observing the channel, only the channel, and then we're like deciphering something from that. We don't know the inner workings of the keyboard, but it would be interesting to like look at the actual code of the keyboard if we can get it off the chip, which we should be able to, I assume. I don't think there's going to be like any big security measures going on in here. But yeah, I mean, kind of let me know what you guys think in the let me know what you guys think in the chat and in the comments generally. Yeah, I'm not sure about it, but it's something that I think would be really fun. MCU will probably be locked. I mean, you think that, but but yeah, I mean, like why would you lock a keyboard firmware? Like most of the time people don't do it. It's, you know, in like pretty much all devices like of a certain kind, like if it's not critical, there's no real reason to like disable debugging or disable JTAG or anything like that on a device, because it's useful to, you know, it's useful up until the moment that you send the devices and people start buying them. You can not reverse engineer, you can debug the units that people actually use. So most of the time people don't take the debug ports off because it's not that much you can do. Even if the firmware was locked, I actually I got a really nice book recently. I just changed jobs, and my old colleagues they gave me some actually really nice leaving presents from work. And one of the things that they got me was this this book called The Hardware Hacking Handbook by Colin O'Flynn and Jasper van Woudenberg. And it's basically a book about fault injection attacks you can do on hardware. So this is basically like you open up you open up the hardware and you see the chips and stuff, and you mess with things like the voltage level and the clock rate and all things like that. And if you inject these faults into the device, you can actually make it behave in ways that it's not supposed to do. You can make it do things like skip instructions or change its internal state. And if you do that, what you can actually do is make it skip the instruction, for example, skip the instruction that disables JTAG. Because they will have it on by default for sure. They'll probably just turn it off at some moment. So that's one of the things you can do, even if they lock it, but I don't think they will. Anyway, I'm not actually set up for doing fault injection attacks at the moment, but it's definitely something that I'm interested in doing in the future. So, yeah, indeed. And like this book, I know Colin O'Flynn. I follow him on the Twitter, and I've seen some of the presentations he's given, and his whole like thing at the moment, and has a whole business around it as well, is all about fault injection and that kind of thing. He's done a lot of academic research into it. Now he's building products and tools for doing fault injection, and yeah, he's literally like written the book on it. So yeah, it's a good source. I'm really interested in trying some of this stuff out just for fun. Yeah, I think for the last part of the stream, because I'm gonna wrap it up probably in the next 10 minutes or so, but one of the last things I'd like to show you, if you're interested, is just a little look at this Ebpf script of like how we're actually doing this kind of Where is it? Let's run this ebpf again on the keyboard. 100% sure. Make sure that I'm not showing the keyboard cam when I type my password in. Alright, yeah, so like basically you see now I'm getting a load of packets out. That's this ebpf script, and I think it's pretty cool to take a look at. So yeah, so I'm going to open up, I think I'm just going to open up in this window. I can't wait for the time where I don't have to type tilde into my thing all the time. Where is this? Ebpf USB, ebpf USB.py. Yeah, so this is this little script that is Troft. I also saw this video by Joe Grant, doing the fault injection attack against the Tresna wallet. Super interesting. Yeah, Joe Grant's great as well. He also makes some really cool tools, like the JTagulator tool. So yeah, this is basically a Python script, and it's got some options here. This is just so you can pass in the vendor ID and the product ID and stuff. That's just like passing that stuff out. And the real meat of it is that there is this sort of like embedded C code inside the Python. And you can see that there is an include here that is from Linux USB. So that's the actual... Hey Daniel, if you just made it. We're getting to the end of the stream, so it's a little bit of a shame, but it's really nice to see you here anyway. We've been doing some real some real trudging through USB packets. So we're including a header file from the Linux kernel here. So we this is really code that really runs in the kernel and gives you access to all of the stuff that's happening in the kernel, pretty much. There are quite a lot of limitations actually, but the limitations are there for the safety aspect, and that actually, when you're running an operating system kernel, you don't just want people just jamming any piece of code that they want into the system. Because you can bring down you can actually crash the whole computer, and you can do some real damage. You can brick the system basically. I don't think you can brick a system directly, but I mean maybe you can. But anyway, you want to be careful about the kind of code that you can run in the kernel. And up until now, well not now, but up until eBPF was a thing. The way that you could get code to run in the kernel was either that you literally worked on the kernel, right? You wrote code in the kernel. That's a problem because you need to get that synced up with Linux, or then you have some weird fork. The other thing you can do is write a kernel module, and that's what USBmon is. So USBmon is a kernel module that you can load into the kernel while it's running, and you can unload it. But if your kernel module crashes, you can still crash the kernel. You can still do real damage in the kernel. And there are these other problems that come with kernel modules, that they're not really a flexible solution. They're not really great for hot swapping, all this kind of stuff. eBPF is kind of a slightly different approach to this whole thing. And it's basically, you write this piece of code in C, basically C, and that gets compiled by a special compiler for eBPF, and that turns it into a special kind of virtual machine. And importantly, that the instructions of that virtual machine are not Turing complete, which is a whole discussion we actually had earlier in the LLJS Discord channel. There's a link in the description if you want to join. And so it's actually not Turing complete. You can't make infinite loops in this, for example. And I don't know exactly all the details about how they go into verifying all the things that can and cannot work in the eBPF. But suffice to say that it's like a very small sandboxed situation for actually allowing you to run code in the kernel. And the really cool thing is that even though it compiles to a kind of virtual machine bytecode language, when you actually load this code into the kernel, so when I run this Python script, this code is being loaded into the kernel through a special system call. That code, the bytecode, gets compiled to real code, like just in time, as you load it in. So it actually turns into your native machine instruction. So in this case, it turns into x86-64 assembly code and runs. But it's been verified that it doesn't have all these crazy things like infinite loops and arbitrary kernel memory reads and all of these like things that would make it unsafe. It doesn't have any of those things, so it can actually be turned into real code and run at native speed. And this is one of the amazing things about it. And like, I'm completely in love with this technology. I think it's amazing. I'm gonna like try and do a whole lot more with it, actually, just for fun's sake. But in this case, what we're actually doing is we're bringing in this header file from the Linux kernel, the USB part, and that gives us access to a bunch of the data structures that are available to the USB, and like the data structures that wrap up USB packets. And what we can actually do is basically define a data structure that we're gonna get back into our regular program. So that's what this is. This is like an object basically where we can keep track of like some things about like how long the buffer is, right? So if we look here inside the terminal, we'll see that we get this this buffer, and this is the buffer we're talking about, right? This data that we see in this like little hex dump. So it's got an actual length and a buffer length, and those are properties here in this data structure. So this is the actual length, this is the buffer length. We also have like the vendor and the product ID, which are just part of USB. We've got the endpoint. So we talked about endpoints earlier, right? That's the place where data is exchanged between host and device. We've got the transfer flags. So that's like some internal information about like kind of what's going on in this transfer. And we have some attributes about the endpoint itself. I need to make the naming consistent here. I kind of like started off with the base of someone else's code. I'll make sure that the link for this repository is eventually in the description. It's not going to be in the description now, but I'll make sure that it is in the future, and you can just come by the Discord channel to ask for the thing. But this you can find the original repository that I based this on, and this is why some of the naming is inconsistent, because I've adapted my own bits and pieces. So this is some attributes, and then eventually we have like a buffer that holds like this actual data that we're exchanging, like that we're grabbing the packet from the from the USB device, and it's like 4 kilobytes this packet, because even though like we're looking at 8 bytes from like a key press on the USB keyboard, like some devices will send more data than that. And I think like generally most of the devices that I encounter, they're sending like maximum of 4 kilobytes at a time. But I need to look into that for like things like the microphone and the camera, because it's probably a lot more. But for those devices, I don't really need to. I'm not going to introspect them that much. So there's kind of a trade-off to be made here, and this could actually be done at build time. So we could set a flag to say the packet size is 4K or the packet size is 2K or whatever, and we could have that at the moment that we put this Ebpf program in the kernel, which is one of the really cool things. So so what you actually do is you define a function, and that function, the name of that function kind of instructs the compiler where it should hook this thing into the kernel. So this is a kprobe, which means we're going to attach to a specific function within the kernel, and that function is the USB HCD giveback URB function. So there is a function named this in the kernel. And what we get when we run this is we get something called a URB. And if you remember from Wireshark, that this name URB was all over the place. And I think I don't remember what it stands for, but it's like USB request something or something like that. It's like some internal packet that's used within the kernel. And so what we actually do in here, it's a really short program. It basically kind of don't need to worry too much about this stuff. It's basically setting up this data structure. It's grabbing the USB device from this URB data structure, and then we're just copying a bunch of its properties into this data structure. And then we copy a bunch of memory from the kernel, which is the actual buffer itself. Oh, Daniel says it's the USB request block. Yes, Daniel is something of a USB expert. He's building a really awesome device that translates keyboards to like legitimate Switch controllers for playing competitive games. It's really awesome. You should totally check out that. And I'm gonna, if I remember, I'm gonna also leave a link in the description to that. But yes, thank you, Daniel. So it's a USB request block. And yeah, so what we actually do is we copy some memory out of the kernel into our own data structure that we can pass back. And this is why there's a very specific interface here, because this makes it safe, right? So like we have to be super explicit about any like reads and writes that we do with kernel memory. And then what we do is we basically submit what's called a performance event, because this is mostly for event monitoring, but you can actually also do functional stuff in these. So we submit a performance event which contains like the data that we've built up, which is just this object. And then kind of what happens is down here we've got a Python program, and we kind of create this BPF object. The text is this code that we've defined up here. And what we basically say down here at the bottom is that we're going to open a performance buffer, and this is the callback, like the print event. And then we go into an infinite loop that basically polls that. It just keeps checking if there's anything in that queue. And so what we're doing is we're running this print event every time that this line of code gets executed in the kernel. And what all this does basically is like print this information to the screen for us. So it's just building up a line of data that contains all the information we see in the terminal here. So like the packet number, the vendor and the product ID, the stuff about the endpoint. So what's the endpoint number? Is it an in or an out endpoint from the perspective of the host? What kind of type is the endpoint? So is it an interrupt? Is it a bulk? Is it a control? And yeah, and that's basically it. It records some information about the buffer length and eventually just dumps out the actual buffer. And the rest is just some surrounding code to kind of turn some of the things we get out of the kernel, which are just numbers, into strings, so we can get things like the control or the bulk or the interrupt or the isochronous endpoint types. And it also does a couple of things like disabling input on the terminal, so you can't mess up the input stream while you're reading it out, but that's kind of optional. But yeah, this is really cool. I'm super excited by this technology. I think it's like I think it's such an amazing concept that you can just like write these programs that go into the kernel, and then you've just kind of got like you've got access to everything, so you can really watch all of these things which happen behind the curtain of your computer without having to be some expert kernel hacker, which, you know, I'm definitely am not. But like I feel confident to, you know, write this kind of program and inject it into my kernel and just like poke things around, because I know that, you know, there's within reason, and I should be careful, but with it, like there's only so much that can go wrong this way. The barrier to writing one of these programs is so much lower than it is if you write, for instance, a kernel module. And I just think that's so cool. And you can also do really cool things like this, which is because this is Python, I can do things like Python string formatting. So I can actually, depending on the arguments which are passed to the script, I can actually generate a little bit of C code here, which checks the vendor ID and the product ID and stuff like that. So I can do filtering I can actually build filtering into the eBPF program itself at the time we run the script. So it's not like we always have to pay the cost of doing this check if we want to watch all the USB traffic. And if we only care about the vendor ID, then we don't have to pay the cost of looking at the product ID, for example. So I think that's super cool that you can also kind of do this like meta programming stuff on top of it. That can probably go too far as well, but for now, I mean, it works out really great. Like, you can introduce all of these filtering concepts, which for me in this tool is like the most important thing. So that is like, that's pretty much it. That's like the little crash course that I, in eBPF. You can see this program is like less than 200 lines long, and a bunch of it could be cut, like if you just really want this core functionality. So this is on GitHub already. If you're interested, go and take a look. Yeah, so I guess that's pretty much it. If anyone has any questions or anything like that, now is the time to ask, because I think I'm going to wrap up after this. Daniel mentioned not an expert or just know enough to make my adapter. Thank you though. Well, I'm sure that in the process of making the adapter that that you gained quite a lot of expertise, because yeah, I think you probably have to get pretty deep into it in order to bring that together. Cool. I'm glad it cleared. Well, it makes sense to people at least. I think this is a really, really cool piece of tech, and yeah, again, thanks to Nate to put me onto it, because I never would have even known about it before this. And now that I do know about it, I'm kind of thinking back and trying to realize if I have heard this like thrown around but just didn't know what it meant, and so kind of it slipped out of my brain. And I watched a video from Andreas Kling a while back, which was about doing some kind of like performance, like doing some things with performance events, and it seems that there's something kind of similar going on here, and I wonder if he mentioned something about it then, but not sure. See, Pada K has a question. Will you continue the RISC-V series? Yes, I will continue the RISC-V series. I do plan on picking it back up. At the moment, I mentioned this in some other places, but at the moment, the reason I've been doing mainly only these streams in the past couple of months, or past month and a half or so, is basically that I left my old job, and I've been in the process of doing a lot of interviewing and speaking to companies, and I've just gotten a new job, and so that's been a really kind of time-consuming process, and that also joined with the fact that I have a family and everything like that has meant that I basically haven't had the time to spend making and planning the videos. And yeah, the planning, especially of those RISC-V videos, there's quite a lot of planning that has to go in ahead of time. Kind of need to work out everything I'm going to do before I do the video, before I go into it. Which is a little bit different from these streams, because I just come into the stream and, maybe I've done some prep, maybe I haven't, and I just start like writing the code out. And then that means that everyone has to suffer here when we hit bugs, but yeah, it's kind of the same in the RISC-V as well, but yeah, basically there's more preparation involved. There's more reading. Like, I'm doing a lot of reading of the spec and like kind of working things out. I'm talking to other people, just trying to get to the point where I know everything and have some idea about the design going forward. And so that's pretty much why it's been on pause for now, and I plan on picking it back up. And there's a bunch of stuff, like there's also the compression videos, and I've got this whole thing like ready and done and prepared for like Huffman coding, like ready to go. But I just haven't made the video yet because I want to make that video in a way that is like relatively, like a relatively short video, quote unquote. So yeah, I will get back to it, is the long answer. I'm just catching up with the chat now. So Nate says, it's a deep rabbit hole. U-probes are crazy too. It's its own ISA. Yeah, I've only like briefly heard about the U-probes. So this is like the user probing stuff when you're probing into userland functions, right? But you can basically do the same introspection. But yeah, that's really interesting. I haven't looked too much into it. It must be a completely different way of doing it as well. And you can target it from LLVM, so you're unlimited to C. Oh yeah, that's a great point. Yeah, I saw that it's LLVM has a backend, like Clang has a backend for the eBPF. So indeed, yeah, anything that can target LLVM can. I guess you know all about that. I guess you're doing some. Have you written some of this stuff in Rust as well? It would be pretty interesting to see. Thanks, Pada. I appreciate that. All right, so I think I'm going to wrap it up here. Thank you, everyone. Thanks for joining today and for watching along and for commenting and everything. It's really fun to do these streams and basically sit with a group of people in the room who are also interested and want to hack on USB stuff. So it's really cool. I definitely still want to play around with some other bits and pieces. I have this the limiting factor often with some of the projects that I want to do here is that I always want to frame some amount of it around JavaScript and TypeScript because that's the channel. But I have, and I saw someone mention something earlier in the chat about like hardware USB stuff, like doing reverse engineering more from the hardware side. And I've mentioned this before, but I've got this really cool board from Great Scott Gadgets. If my thing will focus. Yes, so I've got this really cool board from Great Scott Gadgets called the Great Fet 1. And I've got some links in the description about this. This is a really cool board that can basically it can kind of do like hacking on USB devices from both, like you can pretend to be a device host, so you can pretend to be the computer that the device is hooked up to, and you can interact with the device and see what it like. Kind of you can interrogate the device from the other side. Which is a really interesting way of doing reverse engineering if it's not like this, right? This is easy to do because I plug the keyboard into the computer and the computer is I control the computer. But if, for instance, like we had some kind of device and it plugs into some other kind of device, which is also sort of an embedded device or something like a TV or something like that, which also has a USB port, or even a Nintendo Switch, which may talk to the hardware differently than the computer is actually talking to it. Low-level cinematic universes. Yeah, okay. That is... I'm going to have to change the whole identity of this channel, or maybe just create a whole series of different channels. But this device is super cool for that. So basically you can plug a device in, you can script from Python. It's got two USB ports, so one of them goes into the computer and you control the device from that, also in Python. And the other side goes into the device, and so it's super interesting. I bought Daniel says that he bought a Beagle board to act as a man in the middle to just what you're describing. I actually also have a Beagle because I also wanted to see what the Beagle could do in this space. Like I'm super obsessed with like USB hacking at the moment, so I've been getting my hands on all of this equipment that is that BeagleBoard was actually one of the other presents that I got from my colleagues when I left my old job. So they know me really well there. Apparently, it was was a really good thing. But yeah, this is like this is one of the sides you can do. But you can also you can also use this device to pretend to be some other kind of USB device. So I can, like, via Python, describe a device on this thing and then plug it into something else and have that device talk to it as if it were whatever. So maybe I can pretend to be this keyboard, and I can, you know, I can send some faulty stuff to the Windows driver and see what it does. You know, maybe the Windows driver completely melts down if I send it the wrong stuff back, or I can just make it crash in an interesting way. It's a pretty cool attack surface. Like, there's a lot of, this is so off in the weeds at the moment, but like, just while we're here, there's a lot of things you can do if you have something like a TV and it has like firmware updates that you use, like a USB mass storage device. Like, you plug in a USB key into the TV and then that does some kind of update on the TV. Well, one of the things you can do is like have a device like this, and usually what the TV will do is it will do a check to see that the firmware is legitimate, like it was made by Samsung or whatever, whoever makes your TV. So the way it does that is it reads the file, and the file is going to contain some sort of signature, and it's going to check the signature. But because of the way that this stuff works, what often happens is the TV will read the file from the USB stick. It will perform the signature check, and then what it will do is actually read the file again and then install the update. And so what you can do is you have a device like this. You can pretend to be a USB stick. You can supply a legitimate firmware the first time it asks for one, and then the second time that it asks for the firmware, then you give it your fake firmware, or like the firmware you've written, you know, or you've hacked or whatever, like whatever you want to do. And the TV doesn't have like any clue, so it just installs that firmware as the update. So this is one of the super cool things you can do with this kind of like hardware-based USB attacks. But yeah, the problem, of course, is that the Great FET, for instance, only has a Python interface. So I would have to go in and like write a whole JavaScript backend for it, which is possible, but definitely time-consuming. So in order to do that, yeah, it would be a lot of work. And the problem is that like this is like a whole stack of stuff. So the Great FET is like the base, and then there's like a series of libraries on top of it called Face Dancer, which kind of like provide the USB man-in-the-middle functionality. So yeah, that's that would be a real adventure to do that kind of stuff. But it would be really hard to do it in JavaScript. Anyway, if any of you have hung on to this point, thank you very much for watching, and I really appreciate it. Thank you to everyone who's also a patron. I do really appreciate that as well, and it allows me to do some of this kind of crazy stuff. It also allows me to buy something like, you know, this nicer camera that is now on, because before I was using this kind of camera, which is less nice, with less quality and less dynamic range and all that kind of stuff. So that's it for now. I'll see you next week probably, and I guess we'll continue with USB hacking. But if there's something interesting in the meantime, or I feel like shaking it up, maybe we'll switch to something else. But that'll be it for now. Thanks, guys. I'll see you next time.